Hello everybody. So what we're going to be looking at today are secants and cosecants graphing. This is going to be the last graphing section, which I think you'll be happy to see after having looked at like 5 lectures in a row of this stuff. So yeah, let's see how it goes. Now I think we're going to be taking this in a little bit kind of less detail than the previous ones, and we'll focus more on how to solve the problems and stuff that you're going to see on your homework, and hopefully that'll work out okay. So here's the idea. So for graphing secants and tangents, so for graphing secants, and I said tangents, but I meant cosecants, you want to know this, right? You want to remember this. So what do you want to remember? You want to remember that the secant of x is simply 1 over the cosine of x. And you want to remember that the cosecant of x is simply 1 over the secant of x. No, it isn't. 1 over the sine of x. Okay, so that's really the most important thing to remember, because when you're graphing these, what you do is you basically just graph the cosine or the sine and then know how it's related to the secant or the cosecant. So let's look at it. So let's come up with the graph of the secant x. Let's see. Y equals secant x. All right. Now, like I said, we know that this is actually 1 over the cosine of x. So just looking real briefly at the unit circle. I don't want to spend forever doing this, but spend a little bit. Okay. There we go. So let's say that that's a unit circle, right? Then what's going to happen as you go around the unit circle is, you're going to be here, label this, that's a 1, 0. A little bit later, you're going to be here. Let's say that that's root 2 over 2, root 2 over 2. A little later, you're going to be here. That is 0, 1. Then you're going to be over here. Negative root 2 over 2, root 2 over 2. Down here, which is going to be negative 1, 0. Going to be here, which is, looks like negative root 2 over 2, negative root 2 over 2. Oops. Going to be here, which is 0 minus 1. And then finally here, which is going to be positive root 2 over 2, negative root 2 over 2, and then back up to where you start, right? And so that is enough of the unit circle just to point at when we need it. So let's go ahead and figure this out a little bit. So the graph of the cosine looks a certain way. How does it look? Let's see. So cosine. So I'm going to label these as, let's say, pi over 2, pi, 3 pi over 2, 2 pi, 5 pi over 2, 3 pi. And then the other way, skipping 2 boxes at a time. Negative pi over 2, negative pi, negative 3 pi over 2, negative 2 pi. Okay, and so just plotting the cosine on here. So this is going to be plotting the cosine, not the secant. So the cosine looks like this. You have, and I want this to be 1, and I want this to be minus 1. Okay, so the cosine going around the unit circle, right? We're going to start right here, and the cosine is the x value. So we're at 1, right? The x value is 1 right there. Then I'm going to go up to here, and at pi over 2, the x value is 0, so that's right here. And then at pi, you are here, which has an x value of -1, so that's down here. And then it's back up to 3 pi over 2, sorry, back up to 0, then up to 1, and then back to 0, and then down to -1, right? And then on the negative side, it works the same way. So 0 there, -1 there, 0 there, then back up to 1. So when you go to plot this, right, we know what this looks like. You know, this is going to be messy because I'm messy. Okay, good enough. All right, now that's not the secant. That is the cosine. All right, but we can use that to come up with our graph, because what happens is this. First of all, 1 over the cosine. We have 1 over the cosine. So what happens when the cosine is 0? When the cosine is 0, there's a divide by 0, right? When cosine equals 0, 1 over cosine is not defined. Specifically, what happens is you end up with vertical asymptotes there. You get vertical asymptotes at, well, every one of the points where the cosine comes up 0. So there's one right here, right? Pi over 2. So that's pi over 2. Then, and also one at -pi over 2 as well. So x equals plus or minus pi over 2. They're vertical asymptotes. But then there's another one at 3 pi over 2. There's another one at -3 pi over 2. So plus or minus 3 pi over 2. And that pattern continues on, right? Plus or minus 5 pi over 2, plus or minus 7 pi over 2. So this same sort of thing happened for tangents, right? Tangents had vertical asymptotes as well. But what happens is in between those asymptotes, the graph is a little bit weird. So as you get closer to the asymptote, the secant is going to go to infinity. It's going to jump up to infinity or down to -infinity. But let me just pick a couple of points here. So this is not, actually I don't want to number it there. That's not what we're doing. Let's just work out a couple of values, right? Like what is secant? That's too bright to read. Get a different green. Like what is secant of, what is it? Pi over 4, for example. Secant of pi over 4 is 1 over the cosine of pi over 4. The cosine of pi over 4 is square root 2 over 2. So 1 over square root 2 over 2, which is 2 over the square root of 2, which is the square root of 2, which is approximately, I need a calculator for this. I have a new calculator. Got it on eBay. Don't know how to do it, how to use it. So wish me luck. Square root, there's a square root button. Calculators have those, I hear. 2. It says square root 2. Fraction to decimal. 1.14, etc. But about 1.4, right? Now, come up here and say, well, where is that on your graph? Well, pi over 4 is right here. And 1.4, well, that's bigger than 1, right? So like 1 is here, so this is 2. So where is 1.4? Well, 1.4 is about right here, right? Just less than 1.5. So we have that. What is cosine of 0? Oh, sorry, no, not that. What is secant of 0? Secant of 0 is 1 over cosine 0, which is 1 over 1, which is 1. So the cosine goes through this point. And then what is secant? Secant of negative pi over 4. That is 1 over cosine negative pi over 4, which is 1 over root 2 over 2 again. So about 1.414. So at negative pi over 4, we're also up around there as well. Now what happens is the secant goes through these points. And as you get closer and closer to pi over 2, I'm not going to plug them in, the numbers just get bigger and bigger and bigger. And it actually goes up to infinity here. So that green curve, that's what the secant looks like. And then in between each set of asymptotes, you get the same thing going on. So basically, so like in between pi over 2 and 3 pi over 2, it goes through this point down at negative 1, and then it's here, and then it's here, and the curve has this shape. In my last oh no, I just want to erase a little bit of it. Is that even possible? No, it isn't. Oh, that makes me sad. All right. Well, this looks really dumb over here, but we're stuck with it. So, looks like that over there. Over here. Looks like that, and so on. So you can easily get this graph on Desmos or something online. So like go to Desmos, clear, clear, clear. I'm going to need to reset my axes here. But if I go y equals functions and I want a secant x, then that looks weird, but it's because the scale goes up to 130. So like if I go like negative 5, well, I don't want to do that. If I go negative 10, 10, and positive 10, then I get a graph that makes more sense, right? So that's a graph of the secant. And if you graph like y equals cosine, it will make sense based on what we just did, right? So there you go. So the red curve is the secant, and the blue curve is the cosine. And so if you have the cosine graph, it's not hard to graph the red curve if you already had the blue curve, right? And that is useful to know. I am going to actually close the Node app, open the Node app, as I often do, so that it doesn't lag. All right, so there you go. So the green graph is what the secant looks like. And I guess I better draw it over here as well. So y equals secant x, all right? Now, they will ask you on the homework questions like this. They'll say simply, on 0 to 2 pi, where is f of x equal 1 if f of x equals secant x. Now I don't know why they do it that way, right? But they do. And so what they mean is, where is secant x equal 1? And so you would have to know from the graph here, You say, well, where is the secant equal to 1 between 0 and 2 pi? Well, 0 is right here, and 2 pi is over here. And so right here, the secant is 1, and right here, the secant is 1. But they say 0 to 2 pi, not including 2 pi, so the only answer is, right, where is the secant of x equal to 1? The answer is x equals 0, 2 pi, 4 pi, 6 pi, etc., and x equals negative 2 pi, negative 4 pi, negative 6 pi, etc. I could have put pluses and minuses, but I didn't. And that would get you all of, all of the points like this one and this one. They're at even values of pi. But if we're stuck between 0 and 2 pi, then the only answer is going to be this one, right? Because all the others are outside 0 to 2 pi. Like even 2 pi is outside 0 to 2 pi because the parentheses means that 2 pi is not included. Right? So this is the only one. All right. Now what else can they do? They can do some similar questions, right? They can say, example, on 0 to 2 pi, where is secant x equal to, what could they do? Negative 1 maybe. Where does that happen? Right? And we know that secant x equals negative 1 at, well, let's just list them all. Where are all of the values where secant x is minus 1? Well, you'd have to come back here, look at your picture, and say, well, it sure looks like it's negative 1 right here, and right here, and right here. Those are the values where it's negative 1, but that's pi, negative pi, 3 pi. It's all the odd powers of, not odd powers, but the odd multiples of pi. So it's like pi, 3 pi, 5 pi, 7 pi, etc. And also negative pi, negative 3 pi, negative 5 pi, etc. All of those, right? So if you're answering the question in 0 to 2 pi though, which ones of those are in between 0 and 2 pi? Only x equals pi. Right? That's the only one in there. So there's only one of them. And so you just need to graph it and then look at the graph. And you can use Desmos or you can just use this graph. I mean, this graph's hard to read, but that's the kind of thing that can do that. Now, another thing that you need to be aware of is, so this is just kind of a fact here. No, I'm gonna do it in the form of a question. Right? It's Jeopardy. We're gonna answer in the form of a question. Do your grandparents watch Jeopardy? Mine do. All right. What are we doing? We are answering in the form of a question. That's what we're doing. They say, here's something that they might ask you. They might say like, oh gosh, I can't think of how they word it. But what they want is there are certain values for the function that the function cannot get to, right? And there are also some values that you're not allowed to plug in. So like here's a question that they like to say. They like to say, what x values are not in the domain of f of x equals secant x. Right? And what that means is, what are you not allowed to plug in for x? That's what they're asking, right? And you have to know, like, those are where the asymptotes are. Those are the ones where the function doesn't exist. So where are the asymptotes, right? We already said where the asymptotes are, but they're asking it in a different way, right? Like there is no secant of pi over 2, right? It does not exist. Because you can look at the graph and see that at pi over 2, you have a vertical asymptote, because secant pi over 2 would be 1 over cosine pi over 2, and cosine pi over 2 is 0. So that's where the asymptotes come from. So you're not allowed to plug in pi over 2. So this is really, when they say what is not in the domain, what they mean is just where are those vertical asymptotes. Okay, so you need to interpret that as where are the vertical asymptotes. And they were at plus and minus pi over 2, plus or minus 3 pi over 2, plus or minus 5 pi over 2, etc. Those are the ones that are not in the domain. Okay, so they make you pick off a list, but you would need to understand. Okay. I'm still looking for the question that they weird. Oh yeah, here's a question that's weird. Question. They say if f of x equals secant x, what values are not possible values of f of x? Okay, and that's a little bit weird question as well, but they're asking it for a reason. So what they want you to understand is that when you're looking at the secant x, look at the graph here where it's easier. Here's the secant x, right? But look in the middle section, right? It starts here at 0, 1. And then down here it's at -1, right? Well, what happens in the section -1 to 1? What happens in there? Right? The secant is never in there, right? It's always greater than 1 or it's less than -1. It's never in between -1 and 1, ever. And so that's what they're getting at there. They want you to know that. So when they say what values are not possible values, we know that secant x is never in -1 to 1. It starts at -1 and it starts at 1. So it is 1 and -1 some places, but it's never between them. So what they like to do is they like to give you a list like this. So example list. They'll say like -2.1, -1.1, -1, -0.34, 0. Right? Like which of these are possible values? Well, the possible values are the ones that are outside of this interval. Oops. They need to be outside of that interval. They need to be above 1, including 1 actually, or below -1 or equal to -1. So which ones are allowed? Is -2.1 allowed? That one's okay. Is -1.1 allowed? That one's okay. Is -1 allowed? That one's okay. But the other two are not, because they're in that middle section where the function does not exist. So not these, right? All okay. So they wanted you to understand that. So basically they just wanted you to know this graph, where the green section that I drew there is like no man's land. There's no secant in there, in between -1 and 1. All right. So that's a lot just for like the basic secant. Okay. we need to do the exact same thing for the cosecant. So what we have to do is what I just said, the exact same thing, but for the cosecant. Literally everything is identical except the exact numbers. So, you know, it should make sense. So let's do y equals cosecant x now. All right, so y equals cosecant x. So you want to know y equals cosecant x is 1 over sine x, right? So that means if I draw my graph here, I'm going to put like kind of the same values on here. I want to put them kind of light, maybe. Pi over 2, pi, 3 pi over 2, 2 pi, 5 pi over 2, that was enough, right? And then this way, negative pi over 2, negative pi, negative 3 pi over 2, negative 2 pi. All right, there we go. And same thing here, we want to go up to 1, and we want to go down to -1. Exactly like we did for the cosecant. So I'm going to draw the sine, and I'm not going to go into too much detail there, but sine 0 is 0, then it's up to 1, down to 0, down to -1, back up there, then up top. So we have that. Negative half is same. Oops. I didn't draw it all in one line, at least this time, so I can actually delete it when I draw something wrong. Okay, so there we go. So that is, again, not what we're looking for. That is sine x. We want the cosecant of x. And just like before, there are vertical asymptotes whenever the sine is 0, right? Because we have a sine in the denominator. So there's a vertical asymptote right here, and then right here, and then right here, then right here, and right here. All right, so vertical asymptotes there. And then in between each set of asymptotes, we know what to do, right? Because we've done it already. So what's it do? It goes like that. And actually all the numbers are the same. So I'm not going to go into a lot of detail here. Just going to draw the curve. It's exactly the same as the other one. It's just shifted a little bit to the side, just like sine and cosine are next to each other. Okay, so the purple curve is cosecant x. All right, and so again, it looks just like what we had up here. I used different colors, but everything's the same except the exact numbers that where everything happens. Okay, so let's look at this. So let's just list the same kind of facts that we had to list for secant for cosecant. So we know that, let's see, the values not in the domain of cosecant x are all of the ones where you have those vertical asymptotes. So that's at 0, pi, 2 pi, 0, negative pi, negative 2 pi. So they are at 0, plus or minus pi, plus or minus 2 pi, plus or minus 3 pi, and so on. Those are the ones where they're not in the domain. Those are also the ones where the vertical asymptotes are at, so we can say it that way as well. These are also the x values of the vertical asymptotes same ones. Now, what else can we do? We had to talk as well about where the graph is 1 and where the graph is -1. So we can see that secant x equals 1 at x equals, well, where is it 1? Well, let's look, right? I mean, we got the graph right here. So it's 1 right here, and right here, and right here, and of course that continues on. So what do we have? We have pi over 2, 5 pi over 2. Oh, we got negative pi over 2. Okay. So what are these going to look like? What's the first one? Pi over 2. Pi over 2. The next one was 5 pi over 2. What we're doing is we're adding 2 pi to it, actually, if you figure out how far apart those are. So 5 pi over 2. The next one will be 9 pi over 2. The next one will be 13 pi over 2. And if you look at the numerator there, what we're doing is we're adding 4 every time to the numerator, 4 pi. Because 4 pi over 2 is 2 pi. So like that. And also there's negative ones. The negative ones were, what's the first negative one? Negative 3 pi over 2. So negative 3 pi over 2, and then negative 7 pi over 2, negative 11 pi over 2, that's an 11. Negative 15 pi over 2, dot, dot, dot. All right, and so the negative ones aren't the same as the positive ones here because of that little shift where it's not centered at 0 like the secant was. All right, so secant is 1 there. Now, where is the secant equals -1 at? We can write those. Well, it's -1 at a different set of values, obviously. So it's -1 here, and those are the only 2 that we drew. So the positive ones are, I guess the first positive one is 3 pi over 2, although I covered up the over 2. So we have 3 pi over 2. And then the next one will be 7 pi over 2, 11 pi over 2, 15 pi over 2, dot, dot, dot. Now, compare this right here to this up here, right? So, like pi over 2, it's 1, 3 pi over 2, -1, 5 pi over 2, 1, 7 pi over 2, -1. So it alternates. Plus and -1 at those values there as you move across. Now it's also -1 at some negative values of x. That's this is the first one, and that looks like negative pi over 2. And actually, then it'll be negative 5 pi over 2, negative 9 pi over 2, negative 13 pi over 2, etc. Now I think you're only going to have to look up a couple of these a couple of times on the homework, but it's just nice to have them listed here. So you can just get them from the graph. And we can also say just like you know, f of x equals secant x for, I'm going to say f of x again. I don't like saying f of x, calling it 2 different things, but oh well. Just like for f of x equals secant x, for f of x equals cosecant x, you know, the function value is never in -1 to 1. Same rule, right? We didn't look at the graph formally over here, but let's look at it here. If I change this to a cosecant x, functions, that's a cosecant inverse. That is not what I wanted. Try again. Cosecant x, right? Same thing. It, like that green section, -1 to 1, it's never in there. Never ever. So same rule. All right, now that's everything I think that you would need to know about the basic cosecant graph and the basic secant graph. Are you done with your homework if you know that? No, you're not, because they're going to make you do all that shifting stuff again. And that's where I want to be just kind of concise and hopefully, you know, get across the information that you need. And so I would really advise like not graphing these. That's the key. So the key to graphing these is not graphing these. Right, here's what I would do. Let's see. So consider y equals either secant bx minus c plus d, or y equals a cosecant bx minus c plus d. Either one, right? And we need to look at the graphs. So we want to see what the numbers do. So the A, you know, makes the graph taller. It's a vertical stretch. So you want to think back to those basic transformations. Right? So, yeah. So what I mean by that is, let's see if I can draw, ooh, it jumped. So like, if you're graphing one of these, right? Like if this is, that's a 1 and that's a -1. So like if you're trying to graph these and, you know, it looks like this. If this is y equals secant x, and you wanted to know what y equals 3 secant x looked like, then actually I'm going to change that to a 2 because I don't want to draw the graph very big. If you wanted to know what 2 secant x looks like, it's going to be the exact same graph, except that instead of at 1, instead of at 2, it's going to be up at 2. Like that. And then same thing down here at -2. Right? And so you got this middle section here, right, between -1 and 1. Well, now the middle section is actually between -2 and 2. And it's honestly going to help you a lot just to think of it that way. And I'm going to do some problems and you'll see. So that's what the A does, is it stretches out that space between them. Okay? Now, the B is, we know, is not vertical anything, is a horizontal compression. What's that mean? It means that, like, so for example, y equals secant 2x is twice as skinny as y equals secant x. Right? And I'm not going to draw a picture of that because it's just a lot easier to see on a real graph. So I'm just going to say that and then come here and show you. This is a cosecant, but everything for the cosecant applies to the secant as well. So like, if I put a number here like b and a slider, then when b is 1, that's the normal one. But if I make this bigger, right, it makes it skinny. Bigger the number, the skinnier the graph. If it goes less than 1, then the graph starts getting stretched out wider. Okay? Now it's important that you understand that relationship, because when you're graphing these, it's a lot easier to say, oh, it should be twice as skinny, and then move a point on your graph. So that's why I'm saying it this way. Horizontal compression, think of it that way. And then you have phase shift, right? C over B is phase shift, right? That's, so the whole thing moves by C over B on the x-axis horizontally. All right, and then the D, you know what the D does is it moves up and down. Okay, now the reason I'm listing them this way instead of the way we did them in the previous one is because I think it's easier to do problems this way. So I'm going to try to get to the homework, and I hope this works. If I have to, I will use an actual computer, but I hope this works. I should probably close my homework there. That's not our class. This is our class. Homework. Preview. All right. So we could look this up, but I'm going to cheat. I hit and cheat. Okay, let's just do this one just to remind you. Which of the following are in the range? So the range means the y value. So which are the range of secant x? Well, everything bigger than 1, right? So this one is okay. The next one's not okay. The next one's not okay. The next one's not okay. And this one's okay. Right? Anything bigger than 1 in absolute value, plus or minus 1. Yay, right? Easy peasy. And then they show you the graph to make it obvious. Continue. Which of the following are not possible? Well, the ones less than 1. Easy. We're geniuses. Not in the domain. Oh, okay. Well, that's harder. But we listed them, but you have to think. I can't think. You could have looked that up in the notes, though, real fast. Not possible values. Oh, we know that. Those are so easy. I'm just trying to get to the graphs. Oh, we should talk about that too. Since a secant comes from a cosine and a cosine is even, then that means that the value, like secant x equals secant negative x. That's another way of saying that the number should just be the same for a secant. How do I delete? Where's the mistakes are made? There's no, there's no delete. How do I delete? Keyboard. Okay, there it is. Thought I was going to do this one and it was going to be easy. Basic. Where's the point? There's no point. Okay, I can't do it. Answer's negative 1.05, but I can't type that in. Oh, there it is. My bad. Submit. Okay. 1 of 6. 6 is a lot. Okay, I'm going to skip these now because I'm just trying to get to a graph for you guys. Okay, when the sine is 1 at pi over 2. Yeah, I'm a freaking genius. Ah, haha. Okay, this is almost what I want. This is not quite what I want. They want us to write out the equation, which we'll do, but not yet. Another one of those. I just want the ones where you drag the points around. You know what I'm talking about. Just give me one. Give me one. Why won't you give me what I want? It's got to be coming up, right? Ah, ha, ha, ha. Finally, this is what I wanted. Okay, so this is what I wanted. So we're trying to graph, what do we, provide your answer. Where's the, provide the question. Okay, there it is. So what you want to do is you want to say, like, look where the 1/2 is. That's 1/2 x. Now, remember when that was where we said the 1/2 is where we had horizontal compression, right? And so like y equals secant 2x is twice as skinny. So if you put a 2, it's twice as skinny. If you put a 1/2, it's going to be twice as wide. So I see the 1/2 and I say, okay, well, I know that that should be twice as wide now. So I just take this dot and I'm going to stretch it twice as wide. So it started at the pi. I'm going to drag it over to the 2 pi. Now that's right. Okay. Now another thing I see is that outside there's a -1. That means down by 1. So I could take this and move it all down by 1. All right. Now the last thing is the pi over 4. And so the pi over 4 is the shift left or right. And the way they're writing it is a little bit annoying there. But if you calculate the phase shift, I think it would be pi over 4 over 1/2, which would be pi over 2. So I think it should be moved over to the right by pi over 2. It's either pi over 2 or pi over 4. I'm going to try this. So I moved it over pi over 2. So hopefully that's right. If not, I'll think about the phase shift a little bit harder. Oops. It must have been pi over 4. All right. So, easy. Mistakes help us grow. That's all right, I grew just now. Just now. All right. So again, you want to just think about the key numbers. So like, start with the 4. What's the 4 do? The 4 out front means 4 times as tall. So I come here and I say, well, take the blue one, which is at 1. Needs to be 4 times as tall. So it should be up at 4. All right. That takes care of the vertical stretch. Now I see the 2, that 2, that is where you have horizontal stretch or compression. It's a 2, that means twice as skinny. So I need to grab the blue point and drag it over to the left to make it twice as skinny. So right now the blue point is at pi over 2, right? If I moved it to pi over 4, I'd make it twice as skinny. Or I can take the black point. The black point is at pi. If I want to make it twice as skinny, I can slide that to pi over 2. So I take the black point, do that, twice as skinny. That's what the 2 does. What about the pi over 4? Can't highlight it, sorry. What about the pi over 4? We learned in the last one that the pi over 4 directly is going to be a left or right shift. So a negative pi over 4 would shift it in the positive direction, and a positive pi over 4 shifts it in the negative direction. Okay, so when you see plus pi over 4, that actually means it needs to go to the left by pi over 4. So I'm going to take the red dot at 0, 0, and it needs to go to the left by pi over 4. So I did it, right? Just one notch to the left. All right, everything taken care of now except the -3. So the -3 just is in the location for a down by 3. So we just grab one of these, probably the red one, and go down 3. And that should be right. Okay, and so notice how I'm doing these though. I'm not writing anything. I'm just thinking, what does each number do based on where it is? Because I don't need to, oh, no. All right, I guess we're done with that because I have to click through a whole bunch of them and it's impossible to pause the video. It's gonna make me start over. All right, well, you know what we're gonna do is I'm just gonna babble incoherently for 30 seconds. What I'm gonna do while I'm doing that is we're gonna get to the first type of graph problem that we haven't talked about yet. And we'll do some of those. But it's gonna take me a few seconds to get there. Yeah. We're almost there, right? This is pretty close. Yeah. Move out of the way so I can click the next button. Okay, there we go. These are the ones that I wanted. All right, now on these, you want to, these are where are going to be a little bit harder, where you have to write the equation for it. So let's go back here. So writing the equation given the graph. All right, so let's see what they gave us. Wish I could just copy the picture and paste it here. Do not believe that that's possible. I'll try it once though. Yeah, okay, I selected it. Now what? Copy. If this works, it'll be a miracle. That's not what I wanted. That's not what I wanted. How do I paste? Edit? Nope. Well, I tried. Okay, doesn't seem to be possible. That's insane though. All right. Oh well, it's impossible. All right, so we're gonna draw it. What do we got? So we got 2 points. Negative 7 pi over 12, or sorry, yeah, negative 7 pi over 12, 0. Negative 7 pi over 12, 0. That's not a button. Okay, there. We have another one, was it 5 pi over 12? Okay, 0. And then somewhere we've got the other one, like the middle section is down at 4. It's not there, it's like over here. All right, and I'm not going to draw this in too much detail. Just gonna cheat. There's, oh no, that can't be right. I should have really drawn asymptotes. Right, like if there's an asymptote and then there's an asymptote, then that's really badly shaped. Okay, good. That's not really good enough, but I'm going to say good enough. We can see what we need to see. Okay, so this is what we have. Okay, now what you want to do is identify what all of these things are based on based on the graph that you have. So like normally, right, what is this space on the original, what is this space on the original secant graph or cosecant graph, right? It's from -1 to 1, right? So that's normally a distance of 2, okay? Now, what is it on ours? The distance from here, man, the lag is killing me. The distance from there to there is 4, right? Now that distance is 4, but you know, on the original graph, okay, this is, I'm writing and it's like showing up like 5 minutes later. Okay. Whoa, it didn't save it. It's fine. So that distance is 4, and on the original graph, it's 2, right? That distance. What's that mean? It means that the graph is twice as tall. That's what it means. So the graph here is twice as tall. All right, what does that mean? Well, that means that the A has to be 2, or technically it could be -2. Why? Because it needs to be twice as tall. Twice as tall means you multiply by 2, right? That's what the A does. The A is a vertical stretch by factor. Okay, so we got that. So we already know A. Now, for B, we need to know how much it's shifted left or right. Well, we need to know what kind of graph we're using. So look at the problem here, and it says we're doing this with a cosecant, it says, right? So we should be comparing our graph to a cosecant. Compared to the cosecant, the original cosecant, I should say. So compared to y equals CSCX, what does CSCX look like? Well, where is it? So that was the one that we did second, right? It's this one. So normally, the point on the left is at -3π/2, right? The peak there, this one, and the one on the positive side is at π/2, right? And that distance is 2π. The distance from here to here is normally 2π. Okay, so I guess I'll have to draw this. I don't want to redraw it, but normally that should be 2π. So the period should be 2π normally. What's the period here? Well, you have to calculate that, right? The period on this graph is the distance between those 2 points. So you have to calculate it as 5π/12 minus 7π/12. So basically you're just adding those together, and you get 5π/12 plus 7π/12 is 12π/12, which is pi, right? So the natural period is 2π. This one is pi. So it's been compressed by a factor of 2. But I'm going to say it in a slightly different way. You can use the formula from sine and cosine for the period, and do it that way if you want. So a sine bx, or a cosine bx for the period, not for everything else. But so the formula, remember, was period p is 2 pi over b, or absolute value b, but I'm just going to say b. So in this case, the period is pi, and we want to know what the b is. So you move the b up, you get b pi equals 2 pi. Divide by pi, you get b equals 2, right? Or the other way was to say that when we got that the period was pi, that must have been compressed by a factor of 2, right? Either way, you get that b is 2. So now we know that a is either 2 or negative 2. We don't know. B is 2. In order to get the c, we can do the phase shift, but they kind of cheat at it, right? What they're doing, you'll notice this in the examples, is they write it this way. Secant or cosecant, I guess we're doing cosecant here. They're writing it this way. They're putting the b here, and then they're doing x minus the phase shift, basically, right there. And that makes it easier to write. So what we would want to do here is figure out the phase shift in order to get that number. Okay, so we just need to figure out the phase shift now. How are we going to figure out the phase shift? Well, the way you want to figure out the phase shift is from where it was at 0, basically, or just how far it's been moved left or right in general. So yeah, that's gonna be the tricky part, I think. So let's look at it here. Let's look at it here. How are we going to do that? Yeah, we might have to fall back on sines and cosines, which make me sad. So the phase shift looks like the one that we can't get easily. Let's get the D though, because that's going to be easy. How far has it been moved up or down? Right, and hopefully you should realize that normally, right, the normal cosecant graph, right, it's like this, where it's centered on the y-axis, right, above and below 0. And when you stretch it, it still stays centered, right, plus or minus 2, that kind of thing. So if you look at this one and you say, well, how far has it been shifted down? Well, how far would you have to move it to make it centered again, right? If it's from here to here, right, if that distance is 4, then it's been moved down by 2, right? Because it probably started like this, plus 2 and then minus 2, and then was moved down to get what we have, which was 0 to 4, right? So it was, right, we have 0 to 4, but it must have started out plus or minus 2 when it was still centered. So I can look at this graph and see that it's been moved down by 2. So I know that the D is minus 2. So I'm able to figure out the A, the B, and the D pretty easily. The C, or the phase shift, if you write it in the form that I've got here, is a little bit mysterious. So what you're going to have to do, maybe, is actually draw in the cosine or a sine and then try to do it that way. So it's really kind of a pain that they're making us do this, by the way, but if you draw in the cosine, right, it goes between the peaks like this. I don't even know if this is going to help us, but it might be easier to visualize then actually this should have been a sine. Yikes. Do we have any good numbers on this graph? I mean, how are we gonna, I don't understand how we're supposed to get a handle on this. Yeah, that's very strange. because I almost want to just do it this way. I mean, this is bad, but I almost just want to go to Desmos, click this to A. Where's my functions? Functions. Secant, cosecant. We're doing cosecant. B, parentheses, X minus, I'm going to write this as a C, but like the way I wrote it, it's actually the phase shift, not the normal C. But like what letter I use doesn't matter. And then plus D. And it's going to say, do you want sliders? And I say, yes. I want sliders for everything. And what do we know? Like we already decided that the A was 2, right? Because it should be twice as tall. Stop that. Okay. And we know that the B was, what was the B? Let's look. Man, closed itself. The B was, where are we? 2 as well. So go to B equals 2. Makes it twice as skinny. The D was, I believe, -2 because it's down 2. Like that. So this is already looking a lot like the correct graph, right? But we need to be able to slide this to the right place. And so if I click on the wrench up there in the corner and I change on the x-axis, I put a pi there. That's just to make it start labeling things in terms of pi. And oh, I didn't know I could stretch it like that. What we need to do now is just adjust the C so that we get them in the right place. So looking at the homework, which is actually here on a different tab, oops. Here, we want the left point at -7 pi over 12, and we want the right point at 5 over 12 pi. So just pick one and then try to make it happen. So like, let's try to make the 7 over 12 pi happen. That's here. So where would 7 over 12 pi be? 7, 12, oh, there it is. I see it now. So zoom into where I can see it, and I should just be able to slide this over to where it goes. Oh, I can't. It's not happening. I don't have the resolution. If we really have to, we'll do it with like algebra. I think they're going to make me, which is really sad. Okay. How can I? Oh, 0.1. I type point 1. Okay. Yeah, it just doesn't want to. All right, well, shoot. Honestly, so here's what I was trying to do by doing that. What I'm trying to do was avoid this, because you can't, with what we've done here, it's not easy to see what the phase shift is, because everything's already been like stretched and everything. And if you draw in the cosine, which is what that orange curve is, sorry, that's the sine. If you draw in the sine, then it's still not easy to tell what the phase shift is, right? So the problem is, all we need to do is know the phase shift, but you can't just look at it and know what the phase shift is like you can with a sine or a cosine. And this one's just been shifted around a lot. So I'm going to hit cheat. You'll see we got all the numbers right except for the pi over 2. Oh, they have a -2 actually. Really? That's strange, but okay. But I don't think that they're going to have a good way to do it. So I'm going to look at their instruction, because I think this is going to be bad. I don't want to watch their video on my video, but I guess we're going to have to. They're doing it for that. Okay, fine. Fine. All right, let's do it. I mean, this is just about impossible. Like, the numbers that they're giving you here are ridiculous. Can I even see the graph anymore? No, I can't even see the graph anymore. You're killing me here. All right. Transformed cosecant. What are the values of B and C? I'm not doing that. I just want to go. Stop. Let me scroll, you cowards. Yeah, pi, okay, blah, blah, blah. We see the midline is at C is -1. Given the general equation, so there is no phase shift. Okay, yeah, they are just flat out cheating on these. These are ridiculous. All right, we're going to do this one from scratch. We're abandoning this one because I didn't draw my graph good enough that I can finish the problem. But we are going to draw this one. Okay. We're going to do it. I hate these problems. All right. So we got to do it again. We got 1/3 pi 3. Pi over 3, 3. Okay. We've got 4 pi over 3, 3. All right. Okay. And then halfway in between, we must be down. Well, no, we don't have to be down anywhere. So what is it? We are up at 1, actually. Okay. So we must have asymptotes halfway between. Like that. And then let us draw the curve. That's not right. How is, yeah, that's what I thought. Okay, so there you go. Now, let's do this hopefully relatively quickly here. So for the ones that are easy. So what we've got is this distance is 2, right? That distance is 2. That's what it normally is, right? So that gap there is 2, which means that that's what we normally get. That's normal. So A is 2 or A is minus, sorry, no, A is 1 or minus 1. Okay. Now, what else do? We need to get the B right, right? In order to get the B right, then we need to figure out what the period is here. On this graph, the period is the distance from here to here. So that's pi over 3 to 4 pi over 3. So 4 pi over 3 minus pi over 3, that's the period, which is going to be pi, right? Then you can use that the period is 2 pi over b. Put the pi in, so pi is 2 pi over b. b is 2 pi over pi, which is 2. All right, so we got that. So we already had a equals 1 or minus 1. We've got b equals 2. So this is going as well as it did last time. Yay. D is how much it's been moved up or down by. So where's the midline on this? Right? This is 1 and it's up at 3. So where's the midline? We haven't talked about midlines for cosecants, secants, but the midline is the way you would always draw it, in the middle. So that's y equals 2, right? So if that's y equals 2, this has been moved up by 2. So the d is also 2, all right? Y equals 2. Normally it's 0. So again, just like last time, the only thing that's going to be hard is going to be coming up with the c. Now, we can draw part of a sine or a cosine in here. I mean, whichever it is. I'm going to draw it. And we're going to have to get something from this graph here. Okay, so first of all, what are we doing? A cosecant or a secant? I haven't even looked so far. So we should be doing a secant function, it says. So we're looking at y equals a secant. We're putting the b here this time. X minus c plus d. We have everything but the c. What we need is to figure out how far this has been moved left or right. So a secant is a cosine. So normally the cosine has its peak at 0, right? The original cosine had a peak right here. Right? Do you remember the graph of the original cosine? Right, starts up at 1 and then it goes down on both sides, normally like that. Okay, this is y equals cosine. Now this one's been shifted, right? The green one that I drew, how far has it been shifted to the left or the right? It's been shifted this far, right? The peak went from here to here. So that's a distance of pi over 3. So our shifted cosine was at pi over 3, which is like this. Okay, so we see the shift of pi over 3 to the right on the cosine. You can't really tell on the secant. So we see a shift of pi over 3 to the right on the cosine, and that means that the c is actually going to be negative. Well, not negative. The c is going to be pi over 3, but then in the form it'll end up negative. So you have to see that shift. So what should my answer be? I should have y equals, we're going to go with 1 secant, b, which is 2, x minus pi over 3, close, plus d, which is 2. So this is what we're going with, okay? And if this is wrong, I'm going to break this Apple Pencil and then have to buy a new one for $120. Okay, what do we got? 1 secant. That's not what I wanted. I wanted to scroll. How do I get a function? How do I get a function? How do I hate this. All right, what is it? Y secant, parentheses, we need 2. Is it 2? I forget. It's not there, it's hidden in the notes. All right, 2 parentheses x minus pi over 3. 2 parentheses x. 2 parentheses x minus pi over 3. We're going to close these parentheses somehow. And then, what is it? Plus 2? Is it plus 2? It is plus 2 on the outside. So I'm going to put a plus 2 and see if that does it. Plus 2. It did not. How do I get that parentheses in there? From the keyboard? It doesn't have parentheses there. All right, I guess it's right. Okay. I think I typed that in right based on what I was trying to do. I didn't type it as a fraction, I typed it as pi over 3. Okay, so yeah, I was trying to type it in this way, but then I just used the division symbol for there. All right, that sucked, right? These are terrible. Now we know. What was the hard part? The hard part was identifying the phase shift. It was actually pretty easy on this one, and the reason it would have been easy on this one is because this point, do you see this point in the middle, is marked at 1/3 pi. And if you compare that to the original secant graph, which, let's scroll up to the original secant graph way up here. The original secant graph actually has this point right here in the middle. So it would have been possible to see that phase shift very easily if I had just looked for the fact that it's in the middle there. Now the reason the cosecant, the first one we did, was so much harder, and I couldn't even do it after I got rid of their nicely drawn graph, I couldn't even do the problem. And the reason I couldn't do that was because you need to be able to see the phase shift, but being able to see the phase shift, if you're looking for this point right here, you need to know, like, you need to be able to identify that point after it's been shifted. But you can't identify it after it's been shifted if your graph is terrible. And so that is why once I deleted it, like, I'm like right here going like, okay, well, the phase shift is, we're supposed to be using a sign, so I needed to know where this was basically. And I have no way of knowing that because my drawing isn't good enough to tell me. And that was the problem. Yeah, that was the problem. Let's do one more. We are like way over, but you know, these are terrible, so I think probably we want to do this. Is this a cosecant? It's a secant. I'm going to do an instructor cheat, and we're going to do a cosecant, because that's the one that we screwed up last time. I'm saying we because I feel like you share part of the blame. Is that funny? Probably not. Oh, I have to... No, I'll try it again. I'll try it again. I didn't want to, but I'll try it again. All right, let's do one of these. We know how to do these. These are the easy kind, right? What's the 3 do? What's the 3 do? The 3 makes it twice or 3 times as tall. So you take this blue dot, and it's at 1, and you move it up to 3. 3 times as tall. All right. What's the 1/2 do? I can't really highlight what I want to. But what's the 1/2 do? The 1/2 is compression by 1/2, which is actually stretching it by 2. So compression by 1/2 is stretching it by 2. So I need to make it twice as wide. Easiest way to do that is to take this black dot, which is at pi over 2, move it over to pi. Now it's twice as wide. Pi over 2 to pi, right? Moved twice as wide. Okay, now we need the 3 pi over 4. The 3 pi over 4 is left or right shift. Because it's a plus 3 pi over 4, it actually needs to move left 3 pi over 4. So you take the red dot, which is at 0, and we need to move it to negative 3/4 pi, right? Because the shift is 3/4 pi left. So you take the red dot and you just move it over 3/4 pi. And right, you can only move it in quarter pi increments, so that's the right one, right? 1 before you get to negative pi. What's left? +1. So the +1 is just everything up by 1. So I think grabbing actually the red or the black dot will work. Just don't grab the blue dot because you'll change the height. So the red dot, and we're going up by 1. All right, did it. These are so much easier than the other kind, aren't they? I thought these were the hard ones, but these aren't the hard ones. These are the easy ones. Yeah. I know I got it. Smart. Okay, well, let's do this one. Might as well. All right, let's try this. 1/2 out front. What's the 1/2 do? Makes it shorter by 1/2, right? Because that's the scale vertical stretch. But a stretch by 1/2 is half as tall. So you take the y = 1 point, the blue one, and move it. You want to make it half as tall. Okay, done. Now there's no number on the x. So there's no number on the x. That means we're not making the graph skinnier and we're not making the graph wider, because it's the number in front of the x that does that, and there is no number, so it's a 1. So all we got to do now is move to the 3 pi over 4. 3 pi over 4, that's where left and right shift goes. So it's a negative 3 pi over 4. That means to the right. To the right by 3 pi over 4. So we just take... Ooh, how do I make this? Okay. So we want it to be to the right by 3 pi over 4. So take the red dot and go right 3 pi over 4, 3/4 pi. So that's 1/4, 1/2, 3/4. What's left? -1. So the -1 is down by 1. So just take the red or black dot and go down by 1. There it is. That should be it then. If I could just make this smaller. Submit. It almost got me again because of the next button. I just want to get to the other kind. Okay, 3 times as tall. Let's do it quick. 3 times as tall. Blue dot up by 3. 1/2 on the x. That means twice as wide. So move the black dot from pi over 2 pi. All right. Plus pi over 4. The plus means left, and left by pi over 4. So I need to go 1/4 pi to the left. So grab the red dot, one notch to the left. Okay. And then +1. That means up by 1. So grab the red or the black and go up by 1. Submit. So easy. Give me the other kind. Just give me the other kind. Please just give me the other kind. All right. Twice as tall. Right? The next 2 means twice as skinny. So black dot comes in. Plus pi over 2. That's left by pi over 2. 1, 2. There it is. -3. That's down 3. Go down 3. Okay, I guess it's only the red dot that I can move for that. Submit. These aren't bad at all. The other kind are terrible. Why? 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 Just give me the other kind. Just give me... Oops. Give me the other kind. Done 100 of these right in a row. I have mastery, I promise. 3 times as tall. It's just never gonna let me do this, is it? Never gonna give me another problem. 3 of 6. Oh no. This is my nemesis. Why does it have an answer in the box? Is this the one that I was supposed... This is the one that we did, but I didn't do, right? Okay. That's good, though, because we can do it right now. Okay, I'm not redoing the whole problem. What I'm doing is I'm just going to say what we should have done. Oh, that is actually still like legitimately bad. I thought we were going to be able to see something, and we're not. Okay. No, you're not going to be able to tell this. This is like, this problem should not be on this homework. Honestly, it shouldn't. Let's look at the problem again. And I mean, we're going to finish after this. This is the one that we're looking at. The same one that I did not finish because we didn't know what the C was. Okay. What they want you to do is this. Let me just erase all this stuff in the middle here. What they want you to do is say, this is what you're looking at on your graph. You need to know how far it's been shifted to the left or to the right. So you draw in your, like the sine or the cosine part, right? That goes between the secant or cosecant part. And then what you're supposed to do is you're supposed to say, well, the midline here, which we didn't draw, but the midline is right here. That's the midline. And this is a cosecant, which means normally it's the sine. So if you look at kind of a redrawing of, like, I'll just highlight it real quick. If you look at a redrawing of this kind of section right here, just the green line and the orange, then what you've got is you've got the green line is the axis that I just drew. Okay, and if you draw the normal sine function does like this, right? And it goes through 0, 0. So that's the midline. Now the orange line has been shifted. That's why there's like it hits right here instead of right here, right? So the orange line goes right here. And then that's the sign that we actually have on our graph. Okay, now in order to find the phase shift, you need to know what this distance is. You need to know what that distance is. And if you knew that that was pi over 3, for example, then you would just say like negative pi over 3 there. And then that would be the answer. I'm not saying it is, I'm saying that's how you would do it. Okay. Now, why can't I do that? Well, on this graph, first of all, right here, I can't see, oops, that's not what I wanted. I can't see what this distance is right here. I don't have any markings on my graph that are good enough to tell me what that is. If I can tell where the asymptote is, I can do it. Where's the asymptote? You see they didn't label it, right? So they didn't label where the asymptote is, so I can't tell where that is. So you say, okay, well, where else could you measure the phase shift? Where else could you measure the phase shift? Well, nowhere. You can't, because it's been stretched. So you can't see the phase shift from, I keep doing that, erasing what I'm trying to show you. You can't do the phase shift from here and from here because the graph has been stretched. I mean, you can, but it's going to be a really roundabout method in order to do it. So you can't really do it there. Okay? You kind of have to do it at the part that's shown. And they didn't put numbers on their stupid graph where that asymptote is, which means you can't see where this purple, where what I have a purple line is. You can't see where that is, which means you can't identify the phase shift. And if you can't identify the phase shift, then you have no way of knowing what this number is. And that is why this problem, as it's drawn right here, should not exist. Okay, it just should not exist. And if you come over here and we have this one, right? This is the one that we were trying to draw, and we had a 2, a 2, a 2, and then you couldn't put this C to the right place. But if you knew exactly what it was, you would be able to do it, right? Because I would be able to type in like pi, and then if I go over, where's over? Over 3, something like that. Is that the right number? I think that's the right number. Then that gives you that at, that's negative pi over 12. This should be negative 7 pi over 12. Where's the other one? What's that? That's 7 pi. Oh, okay. I shifted the wrong direction here. That was supposed to be a plus. Plus. Is that right? No, that's still wrong. It's supposed to go 2 more pi over 12 the other way. All right, let's fix this. It's something over 12. So put the 12 there. Go up there. And 3, is it 3? No, that's not. It's not 3. Is it 4? Where is that? That's 5. Is it 5? No. 6? No. Was it 2? What's that? Okay. Pi over 6. It's pi over 6. Right, because then now that's at negative 7 pi over 12. The one over here will be at 5 pi over 12. The one down here was not labeled anyway, so you don't know what it is. But there. And so you get that in the right place, negative 7 pi over 12. You get this one in the right place, it's 5 pi over 12, and everything else is right. But I basically found that C just by typing in numbers. And the reason I had to do that was because you literally can't see the phase shift on the graph that they gave you. You can't see the phase shift here. And they don't have a good way to measure it based on what they gave you. So this question is more or less completely BS. Yeah. So if you see this, you are going to be in trouble. And I can't delete it, so I'm just going to have to let you know. You're going to be in trouble when you see that. So if you put x, not that, that's multiplied. X minus, what was it, pi over 6? Was it minus? I think it was minus. Submit. No? Oh, because it's negative. That's wrong. Yeah, ridiculous. Let's see how they expect you to do it. So they expected you to see, look what they did. They drew the sign in, and then they said, oh yeah, that's negative pi over 3, and then this one is positive 2 pi over 3. Well, how were you supposed to get that? They just, like, how were you supposed to get that? You needed to know what those numbers were, where they put the black dots. And I mean, it wasn't impossible. Like, I could have done it, but I couldn't have done it in a way that I would expect you to do it. All right. Let's try to do this one. What are we? Oh, we're like, this is going to be a 2-hour video. This is ridiculous. But we'll do this one. And if it doesn't work, I don't know what I'm going to do. Hopefully this works. what do we got? 5 over 24 pi 3. Can't write when it's this laggy. 5 pi over 24 comma 3. Then there's another point. 17 over 24 pi 3. And those are the only points they give you, but they do tell you that the others are at -1. So they're skinny up here, skinny up here, there's one here, all right, so they literally just give you this, right? This is the graph that they give you, not drawn very well. Going to close this and see what we can open it up and try to do it. Oh, come on. When it's that laggy, it just doesn't work. Okay, back. All right, so this is what we have. We've got our ugly graph, and we're going to try to do this. So some stuff is going to be pretty easy, and some stuff's going to be hard. So this is, again, A. They said cosecant, right? Did they say cosecant? Cosecant. So this is the same as the one that we couldn't do. So A cosecant, B parentheses, x minus c, close parentheses, plus d. That's what we're going for. So again, most of it's easy. That distance is 4, right? That's double what it should be. So it's twice as tall, so A is 2 or -2. We can also draw in we can draw the midline in too. So the midline, if it goes between -1 and 3, then the midline is going to be at y equals 1, by the way. All right, so what are we doing? So first of all, twice as tall as it should be. Twice as tall. That implies A is 1 or -1. All right, I'm going to write them over here. Probably we're just going to go with 1. Okay, now for B, we need to know the period. So we know that the period is 2 pi over B. We need to know what the period is. So the period is from here to here. That's 1 period. So in order to get that distance, we're going to have to say, well, what's the distance? It's 17 pi over 24 minus 5 pi over 24. That's 5. So 17 minus 5 is 12. So it's 12 pi over 24, which is pi over 2. Okay, so that's the period. Once you know the period is pi over 2, then you go back up to this equation. Pi over 2 is 2 pi over b. So we bring the b up. B times pi over 2 is 2 pi. So b is 2 pi over 2. So b is 4 when you work that out. So b is 4. C, we're skipping. D is easy. D is going to be the midline, and so it's halfway between the 3 and the -1. So if you need to calculate it with a formula, you can. It's going to be 1/2 of the max plus the minimum, not minus. So 1/2 the maximum, sorry, not the maximum, but it's going to be the 3 and the 1 there, so it's not max and minimum. Sorry, I can't do that. That's the wrong wording. But well, then I don't have a way to refer to those because they don't have names. But it's 1/2 the 3 plus the -1. So 1/2 of 2, so it's 1. So it's been moved up by 1, basically. That's how it got to, but that's how it got to being between -1 and +3. Okay, again, everything's easy except the C. Now, in order to get the C, you have to know the phase shift. The phase shift is unknowable and mysterious. No, that's not true. All right, I need to draw another one of those in there. Let me draw one of those. So we need another one of these guys in here. So we know that in here there's a sine function that does this. Okay? And what we need to know essentially is how far this point has been moved over to the right from where it should be, which is right here. Okay, and again, this is going to be like the last one. I don't think we're going to have a good way of doing it. How would we do it if we just had the sine problem? I mean, maybe that's the best way to do it. Yeah, and we're in the same boat here. There's not a good way to know what that distance is, and we know what the solution says. The solution just gives you the graph of the pink function, the pink curve. The solution just does this. The solution, which we're not going to look at yet, just does this. It's going to graph the sine function, like this. They're going to put a dot right there, and they're going to put like probably a dot right there, I don't know, and they're just going to tell you what that is. They're just going to tell you what that number is and act like you were supposed to know what that number is. And I really don't know a fast way to do it. I don't even know a slow way to do it. Well, I do, but I know a very slow way to do it. And all right, but it is what it is. Okay, let's just do it. Let's just do it. How, like, why is this terrible? Let's do it. So here's what we know. So this is a sine curve. So we're forgetting the cosecant and we're looking at y equals a sine b x minus c. Plus d. All right, so here's how I would do it this way. Now we know certain things. So I know that the amplitude here is supposed to be like 2 and minus 2, or if we wanna, let's just use the numbers that we have on the table. So 3 and minus 1. So everything we did for the cosecant we can still use here. So like the amplitude like was 1. No, the amplitude was 2. Why did I put a 1 there? I put twice as tall, but then wrote that. Sorry. It's 2. So it's twice as tall, so put a 2, sine. The b we know is 4. The x minus whatever we don't know, and then we have the plus d, which is 1, right? So I'm writing everything in the sine that I am going to write in the cosecant. And the only thing is we don't know what the c is. And so the kind of not bad way to do it, but the only way I can think of right now to do it is to say, what about where is this peak? Okay, there's a peak right there, right? And the peak is at 5 pi over 24. So we know there is a peak on our graph of, what is it, 5 pi over 24? 5 pi over 24. Now this is what I was trying to avoid. There's a peak at 5 pi over 24. Now the normal sine function, like y equals sine x function, has a peak at pi over 2, right? Because the original sine function that that gives you this graph looks like this, and this is pi and this is pi over 2. That's on the original one. So the original one has a peak right there at pi over 2. So what that means is you've got this inside right here. You've got this inside right here, the 4x minus c, and we don't know what the c is. But what we do know is that in order to get pi, like if it's a peak when you plug in the 5 pi over 24, then the 4x minus c must give you pi over 2 when you plug in the 5 pi over 24. I'm going to write that out in words. So these three things together basically tell you that when you plug x equals 5 pi over 24 into 4 parentheses x minus c, you must get pi over 2. Because there's a peak at 5 pi over 24. So 5 pi over 24 on this function must be the same as pi over 2 on the regular y equals sine x function. And so that's the logic behind this. So you would have to write like 4x minus c equals pi over 2, and then plug in the 5 pi over 24 for 5 pi over 24 minus c equals pi over 2, and you have to solve this for c. And this is what I was trying to avoid, but we're stuck with it now. So multiply the 4 through. You get 20 pi over 24 minus 4c equals pi over 2. Keep the 4c to the other side, subtract off the 20 pi over 24. So you get negative 4c equals pi over 2 minus 20 over 24 pi, which that's, what is that? Pi over 2 minus 5 goes into both of those, so 4 pi over 6. Actually, so what's that mean? 2/3 pi. Is that 2/3? Oh, wait, no, 8 doesn't go into both of them. Hold on, what's this? What numbers go into both of those? 5 goes into both of those. 5 goes 4, and then, oh no, 5 doesn't go into both of them. 4 goes into both of them. Okay, better. 5 pi over 6. Okay, so you have to do pi over 2 minus 5 pi over 6. I'm using a calculator. 5 pi over, actually, pi over 2 minus 5 pi over 6. Negative 1/3 pi. So you get negative 4c over, no, just negative 4c. You get negative 4c equals negative 1/3 pi, so negative pi over 3. That's from the calculator. Divide both sides by negative 4, you get c equals negative pi over, you're dividing by 4, so negative 12, so you get pi over 12. So that's the c, pi over 12. Okay? So then, we should be able to take these numbers and write our cosecant. So y equals a, which is 2, cosecant b, which is 4. B is 4? I guess so. 4 parentheses x minus c. C is pi over 12. Close parentheses, and then plus 1. And we should check this, but I'm not. Sorry, I already forgot it. Scroll up. What is it? It is 2 cosecant, open parentheses, parentheses. What was it? On the outside parentheses, we have a 4, and then x minus, and it was pi over 12. And I can't close parentheses, but I can go to the end. And what was the last bit? Plus 1. Is that right? Yeah. Now watch this. Complete BS. They're going to show you the graph and they're just going to put a dot at pi over 12 and act like we should have known it. Wait. Oh, see, look, they just, I mean, they wrote it in a slightly different form than me, but see what they did? They just put a dot there and they said, oh, you didn't know that? That was at pi over 3. How did you not know that? They must have a cheating way to do it where they take the period and then it's a quarter period to the right of this point. So like, so I don't know if you can see this. I don't know if I can draw it here, but like from these 2 points, from the bottom of the 2 blue curves, right? If you divided that section into 4, then 1/4 of the way will be that 1/3 pi. And so I feel like maybe they're using that, but they're not even saying what they're doing, and that is ridiculous. So maybe stick to this idea. So here's the idea. So when you get to the C, right, write out what you know, like this. And then just say that if you know where this point is, right here, right, that one, where that peak is on the sine, then just say like, well, okay, the peak was at 5 pi over 24, and you need to make the inside of the sine function here, highlighting it again, you can't see it, must be equal to pi over 2 there. So basically, the sentence that I wrote right here, this, you're going to need the equivalent of that sentence for any cosecant problem that you do. Maybe you should come to office hours and we can do this in a more concise way, or maybe I'll post a supplementary thing with a better way, but I don't know of a better way. So anyway, that was terrible. I will see you next time.